Molecular strength and structure of acids. In this video, you will learn how to compare the relative strengths of the hydrohalic, oxoacids, and carboxylic acids. We have three different types of acids that we'll be discussing in this video. The hydrohalic acids are the halogens with an H+, the oxoacids, which have a central element surrounded by oxygens, and the carboxylic acids, or what you may recognize as the COOH groups that we've discussed. We'll start with the hydrohalic acids, since these are a bit different from the others. When we are trying to figure out the trend, there are two things that we must consider. First is the bond enthalpy. If we look at where we are in the periodic table, we can see that I is furthest down, making that the largest bond, which means that it'll take less energy to break the bond based on size. Since the HI bond is the easiest to break due to enthalpic forces, we'd expect HI to be the strongest acid. The other competing force that we need to consider is how the polarity relates. Because F is very electronegative, it is the most stable as an anion. So this would say that HF is most likely to lose the hydrogen and is therefore the strongest acid. So which force ends up being the driving factor in acid strength? Well, it turns out that the enthalpy determines the strength of the hydrohalic acid. And so HF is your weakest, while HI is your strongest. When talking about the oxoacids and the carboxylic acids, we want to look at the comparative stabilities of the conjugate bases, or the anions. A stable conjugate base, or anion, is less likely to grab a hydrogen from the surrounding solution, meaning that it is dissociated more often, and therefore that species is the stronger acid. There are two different characteristics of the oxoacids that can affect the strength of the acid. The central atom affects the strength, as well as the oxidation number. Let's look at both of these in more detail. The more electronegative the central atom is, the more electron density it pulls from the oxygen atoms. When the acid loses its hydrogen, a negative charge is left behind on the oxygen. Let's look at the bromic and chloric acid as examples. Thanks to resonance, both anions are given some stability already. However, since chlorine is more electronegative than bromine, it pulls more of the electron density toward it than the bromine does, further stabilizing the negative oxygens. Because of this phenomena, chlorate is more stable than bromate, making it less likely to bind to a proton from the surrounding solutions, and therefore making chloric acid stronger, since more of the acid remains dissociated. The other factor affecting acid strength, by affecting the stability of the conjugate base, is the oxidation number. Many of you may not know how to calculate this yet, and if that's the case, there's a simple workaround until we learn this in the redox chapter. The more oxygens around the central atom, the higher the oxidation number. For example, let's look at all the chlorine oxoacids. As we add each oxygen, the oxidation number of the chlorine goes up by 2. As the oxidation number of the chlorine increases, so does the stability of the anion, and therefore the acid is more likely to stay ionized, making it a stronger acid. Let's look at two different functional groups, both of which we've spoken of before. I want to mention this because often students get a bit confused when looking at an alcohol group versus a carboxylic acid group. An alcohol group is simply an OH, and these are effectively neutral species. They are not acids. The alcohol group is actually typically amphoteric like water is. Carboxylic acids, on the other hand, have the double bonded O and the OH group on the same carbon. These are acidic. Let's think about what the main difference between these two types of functional groups are. Just like before, this has to do with the stability of the conjugate base. Let's look at what happens when a hydrogen is removed from the carboxylic acid group. When the hydrogen dissociates from the carboxylic acid group, we are left with a negative ion that has resonance. This resonance stabilizes the conjugate base, or the anion, and therefore makes this group acidic, unlike the alcohol groups. Now let's look at some examples. Within carboxylic acids, there are different strengths based on the characteristics of the attached groups. As with the oxo acids, the more stabilized the conjugate bases, the less likely it will be to bond to the surrounding hydrogens, meaning that the acid is stronger. Aromaticity also lends to stability in the conjugate base. Let's do two examples. In this first series, we're comparing acetic acid with similar acids, but with halogens substituted for the hydrogens. These halogens pull some of the electron density from the oxygens, helping to stabilize the negative charge. Since chlorine is more electronegative than bromine, it has an even stronger effect. And therefore, the acid with the attached chlorines is the strongest because the conjugate base is the most stable. Now let's look at acetic acid when compared with benzoic acid. The benzoic acid has an aromatic R group, making the conjugate base more stable, and therefore it is the stronger acid. After watching this video, you should now be able to compare the relative strengths of the hydrohalic acids, the relative strengths of the oxo acids, and the relative strengths of the carboxylic acids. Please note that unless given a Ka, you wouldn't be asked to compare across these groups, simply within them.